Hello everyone, let me introduce myself and my friend. I am Fitri, and he is Alfan.
Hi.
She is Cynthia.
Hi.
He is Kemal.
Hi.
She is Novita.
Hi.
And the last is Stely.
Hi.
We want to explain our subject about quantum computation. The subject will be divided into 5. There are introduction, entanglement, qubit, quantum gates, and Shor Algorithms. Before we start it, don't forget to like and comment this video. And let's check it out.
Introduction to quantum computing. Computers are getting smaller and faster day by day because electronic components are getting smaller and smaller. But this process is about to meet its physical limit. Electricity is flow of electrons. Since size of transistors is shrinking to size of few atoms, transistors cannot be used as switch because electrons may transfer themselves to the other side of block passage by the process called quantum tunneling. Quantum mechanics is a branch of physics that explores physical world at most fundamental level. At this level, particles behave differently from classical world, taking more than one step at the same time and interacting with other particles that are very far away. Phenomena like superposition and entanglement take place. What can quantum computers can do? Quantum computers can easily crack the encryption algorithms used today in very less time, whereas it takes billions of years to best supercomputer available today. Even though quantum computers would be able to crack many of times encryption techniques, predictions are that they would create hack-proof replacements. The second, quantum computers are great for solving optimization problems.
Quantum entanglement is the phenomenon by which more than one particle, generated together or closely interacted, can start a relationship and the quantum state of each particle cannot be described independently. Thus, the particle cannot be described independently, they become a connected system and measuring one will affect the state of another. This property will be preserved even when they are separated by large distance too. For instance, consider two electrons which are entangled. We will consider spin or position, or momentum can be considered. We will take spin which is angular momentum of electrons sums to 0 when it is generated. Now, we can separate this electron by any distance and measure them independently. If the first electron measured a spin up, then the other one will be always spin down and vice versa. And the effect of measurement happens instantly, which means faster than the speed of light.
I will explain about qubit. First and foremost, what is qubit? Qubit is the smallest information of quantum computing. The difference between qubit and ordinary bit is that while bit represent the binary digit 1 or 0, the qubit can represent 0, 1, and both of them as quantum superposition. In other words, one qubit can store more information than one bit can. This means that with qubit, we can solve a complex arithmetic problem 2 times more faster than with ordinary bit. The image beside me shows that qubit can be in superposition of all allowed classic states. Quantum computing uses qubit with quantum gates and measurement, where computing begins at quantum gates and ends at measurements resulting in classical states.
The building blocks of quantum circuits or model for quantum computation is quantum logic gate. They are like logic gates of classical computing world, but unlike many classical logic gates. Quantum logic gates are reversible. This is because quantum mechanics require a quantum system to never lose information over time, and it must always possible to reconstruct the past. Can you think of any classic gates which will make to the quantum world? And gate will not make it since but 1 and 0, 0 and 1 gives output as 0. Yes, not can make it to quantum world. Not 0 equals 1, not 1 equals 0. This is reversible. If output is 0, then input is 1. If output is 1, input is 0. This gate is known by the name Pauli X gate in the quantum world. It maps 0 to 1 and 1 to 0. Hadamard gates also acts on a single qubit and creates a superposition. The swap gate swaps two qubits, that is 1 0 to 0 1 and so on.
Control gate act on two or more qubits, where one or more qubits act a control for some operation. For example, the control NOT gate or CNOT acts on two qubits and performs the NOT operation on the second qubit only when the first qubit is 1 and otherwise leaves it unchanged. In case of CNOT gate also, we can see that each output is distinct and there is no ambiguity and state can be restored. In an electron spin-based quantum computer, the CNOT gate can be implemented easily. Since the control bit and target bit are close together, and control bit spin have some effect on target bit, and it can decide whether we can flip the target with certain electromagnetic wave. CNOT gate can also be used to produce entanglement state of control and target. If we apply Hadamard gate to control first and then apply CNOT gate, both control and target will be in superposition and entangled together. The CNOT gate is generally used in quantum computing to generate entangled state. CNOT together with arbitrary qubit notation can be implemented in logic function in quantum computers.
Shor algorithm. Shor algorithm is a quantum algorithm for factoring a number n in O log n tree, time and O log n space named after Peter Shor. The algorithm is significant because it implies that public key cryptography might be easily broken. Given a sufficiently larger quantum computer, RSA, for example, uses a public key n, which is the product of two large prime numbers. One way to crack RSA encryption is by factoring n, but with classical algorithm, factoring becomes increasingly time-consuming as n grows large. More specifically, no classical algorithm is known that can factor in time O log n k for any k. By contrast, Shor algorithm can crack RSA in polynomial time. It has also been extended to attack many others public key crypto systems. Like all quantum computer algorithms, Shor algorithm is probabilistic. It gives the correct answer with high probability, and the probability of failure can be decreased by repeating the algorithm. Shor algorithm was demonstrated in 2001 by a group at IBM which factored 15 into 3 and 5 using a quantum computer with 7 qubits. Procedure. The problem we are trying to solve is that given an integer n, we try to find another integer p between 1 and n that divides n. Shor algorithm consists of two parts. 1. A reduction of the factoring problem to the problem of order finding, which can be done on a classical computer. 2. A quantum algorithm to solve the order finding problem.